Welcome to This Explainer. Today, we are diving into something that is going to absolutely reframe how you think about human biomechanics. Presented by Dr. Christophe Delong and Kinexa Formation, we're exploring what they call the grammar of movement. You know, if you've always pictured your body as this clunky machine made up of isolated pulleys and levers, well, get ready to have that completely turned upside down. Okay, let's dive right in. Here is our roadmap for today. We'll start with the alphabet of movement, look at the grammar of spirals, check out the neuroscientific validation, and dive into fascia as our inner wiring. Then we'll see this bodily poetry in art and sport, and finally look at how we're teaching movement to AI. Section 1. The alphabet of movement, moving beyond isolated muscles. To start, we really have to challenge a core assumption about how the human body actually operates. For the longest time, the old anatomy textbook perspective taught us that the brain controls isolated linear muscles in single planes. It was like pulling a single string to bend a hinge. But back in the mid-20th century, Dr. Herman Cobbett, along with Maggie Knott and Dorothy Voss, had this revolutionary clinical intuition. The Cobbett view argued that the nervous system doesn't think in isolated muscles. Instead, it controls global, diagonal, and spiral multi-joint patterns. Actually, scratch the old idea entirely. The brain doesn't have a map of individual muscles. It has a map of movements. Take a look at these intersecting D1 and D2 diagonal patterns. Cobbett figured out that these serve as the fundamental letters of our physical alphabet. Natural movement is literally never perfectly straight. It always operates along these precise diagonal lines to form the minimal units of functional movement. Let's look at the D1 upper limb pattern in action to really get a feel for this. Think about something as simple as bringing a glass of water to your mouth. You aren't just pulling a bicep string. To do this naturally, your shoulder flexes, it adducts, and externally rotates, all while your forearm supinates. You're executing this complex, beautifully orchestrated spiral just to stay hydrated. This D1 pattern is a primitive motor letter used for feeding, protection, and basically bringing things inward. Section 2. The grammar of spirals. The mechanics of natural motion. Now that we know the basic letters, how do they combine to form the physical syntax of our daily lives? Well, this doesn't just apply to our arms. Notice the PNF, or proprioceptive neuromuscular facilitation pattern, in the lower extremities. This perfectly illustrates the spiral mechanics governing the simple swing of your leg when you walk. Your hip flexes and rotates, your knee bends, your ankle inverts. Even taking a single, everyday step is a continuous, three-dimensional spiral. If movement is a language, then the trunk is the subject of your body's sentence. No distal movement, meaning your hands or your feet, is grammatically valid unless the trunk initiates it first. It provides the rotational axis for the spiral to propagate outward. If your arm moves before your core engages, you've essentially made a massive grammatical error in your biomechanics. Section 3. Neuroscientific validation. Science catches up to Cobbett. For decades, these spirals were just brilliant clinical intuition, but then the hard science finally caught up. Let's rapid fire through this timeline. In the 1940s, Cobbett maps out these spirals clinically. Then, jump to the 1980s. Researchers mapping the motor cortex proved the brain encodes movement in 3D spatial directions, not by joint angles. By the 1990s, fMRI imaging discovered motor synergies, proving the brain uses pre-packaged groupings of muscles. And in the 2000s, biomathematical models of optimal feedback control proved that rotating and spiraling actually minimizes physical effort and joint stress. The science overwhelmingly proved Cobbett was right all along. Section 4. Fascia. Inner wiring. The physical network. So, if the brain is sending these spiral signals, what physical tissue is actually making them possible? The answer is fascia. We used to think fascia was just passive wrapping, kind of like biological bubble wrap, but we really need to redefine it now. Fascia is actually a massive, active sensory organ. It's a connective tissue network packed with mechanoreceptors. And astonishingly, anatomical research has shown that the body's major fascia lines, specifically the spiral lines, perfectly map onto Cobbett's diagonal patterns. Fascia is literally the physical wiring for the neurological spiral. Section 5. Bodily poetry, art and sport. Let's look at some universal harmonies. Let's take these clinical concepts and look at the visual poetry of elite human performance. Look at the classical ballet arabesque. It looks like pure art, right? But biomechanically, it's a sublime execution of these PNF diagonals.
The dancer's supporting leg locks into a masterful D2 extension, while the free leg perfectly executes a D2 flexion. The spine extends and rotates, distributing force flawlessly across the fascial network. It's beautiful precisely because it is neurologically optimal.
And we see the exact same grammar in sports. Watch a professional golf swing. Massive power isn't generated by isolated muscle force, but through a perfect proximal to distal spiral sequence. The power starts at the ground, moves up through the trunk, rotates the shoulders, and whips right through the arms. Elite golfers use way less raw muscle force, but they organize their spirals so much better than amateurs do. Let's act as an X-ray for a second here. On one side, you have the visible macro movement. On the other, the invisible fascial and skeletal spirals happening right beneath the skin. The anchoring of the foot, the dissociation between the pelvis and the thorax, the diagonal transmission of energy from the back leg to the opposite shoulder. It is a continuous, unbroken line of kinetic energy.
So why do we instinctively find the arabesque or a golf swing so beautiful? Well, the secret lies in our mirror neurons. When we watch someone move, our brain simulates that movement internally. If the movement is a smooth, natural spiral, our nervous system resonates with it fluidly. But rigid, disjointed movements, they cause neurological dissonance. We inherently appreciate a perfect spiral because our own biology recognizes it as optimal. Section 6. Teaching movement to AI. Translating Kabot into code.
How do we take a century of clinical knowledge and apply it to the future? If we want to teach artificial intelligence to truly understand and analyze human movement, whether that's for sports analytics or physical therapy, we have to stop just tracking isolated joint angles. We must completely redefine movement for the machine. We need to teach the AI that movement is a spatiotemporal phrase, organized in diagonal spirals around a postural axis. Look at how seamlessly this builds into code. We can directly translate Kabot's clinical rules into algorithms for machine vision. Diagonal coupling simply becomes a negative dot product between proximal and distal vectors. A true spiral requires the algorithm to detect simultaneous rotation and translation. And that rule about the trunk moving first, that becomes a strict mathematical timing rule. We aren't just tracking joints anymore. We are literally coding the grammar of movement. Ultimately, the grand thesis of our explainer today comes down to this incredibly powerful thought from the source material. Human movement was never silent. We just hadn't learned to listen to it as a language. So now that you know the alphabet, the syntax, and the spirals that dictate how our bodies are truly designed to move, I want to challenge you. How will applying this grammar reshape your own movements, your clinical practice, or the AI algorithms you build? Thank you so much for joining me for this explainer. Keep learning, keep moving, and I will see you next time.